All right, team 1.4 equations of lines. Here's a little bit more information about our linear functions. We have the general form, ax plus by equals c. Now, here the a, b, and c are constants, meaning they're just numbers. So remember, x and y are only variables and their exponents are 1. We have the slope-intercept form, which we already talked about in 1.3, where y equals mx plus b. Remember, m represents your slope, b is your y-intercept. We also have the point-slope form, where we have y minus a point, the y-coordinate of a point that's given, equals slope times, in parentheses, x minus the x-coordinate of a point that's given. But here, the x1, y1 is any point on the line. It does not have to be the y-intercept like the form before it. Horizontal lines, remember, go left to right like this. They're flat. And they have an equation where your y value is the same no matter what. So we can say y equals a, some number a, and your slope is 0. We talked about that earlier. Your vertical lines that go up and down, your x values never change. So we can say, you know, x equals a. And those are the slopes that were undefined. Now let's remember parallel and perpendicular lines. Parallel lines look like railroad tracks, okay? They go in the same direction at the same angle. So the one thing we know about parallel lines is that they have the same slope. Perpendicular lines cross, but they cross making a 90-degree or a right angle. Okay, so a lot of lines cross, but they have to make particularly 90 degrees. In order for them to do that, there are 2 criteria for their slopes. They have to have, first of all, opposite slopes, in other words, opposite signs. And they have to be reciprocals. So for example, if slope of line 1 is a 3, then the slope of the line perpendicular to it of line 2 has to have the opposite sign. So this one has to be negative, and it has to be the reciprocal of 1/3. So notice they have both the opposite sign and it's flipped reciprocal. So let's review writing linear equations given 2 points on the line. So we want to write the linear equation of the line that passes through the points -3,7 and -6,5. Remember, no matter which equation we use, we need the slope. So the slope, I'm going to subtract my y's. I'm going to start with the 7 this time. 7 minus the 5, those are my y values. -3 minus -6, so that becomes a plus a positive. So I get a 2 on top and a +3 on the bottom. So we have a slope of 2/3. Neither one of those points is the y-intercept. How can we tell? Neither x is 0. So none of those land on any of the axes, as a matter of fact. So we can use the point slope, and we can plug in for any of these y values. Let's just use the first guy here, -3 and 7. So I'm going to plug in a 7 for my y1, 2/3 times x minus a -3 for my x1. Remember, minus a negative is plus a positive. So we get y minus 7 equals, when we distribute that 2/3, we get a 2/3 x plus the 2/3 times 3, we end up with a 2. Add that 7 to both sides. We get y equals 2/3 x plus 9. Now you can also do this using the slope intercept.
form, just be careful not to plug in the 7 or the 5 for your b. Neither one of those is your y-intercept. So let's try that.
So we have y equals mx plus b. So we have y equals a slope of 2/3 x plus b.
And remember, b is the only variable we need to find. X and y represent any point. So we can use that -3 and 7 again.
We could plug in 7 here for the y, -3 for the x. These two reduce. So I'm going to get 7 equals -2 plus b.
If we add the 2 to the other side, we would get b equals 9.
And then we can write our equation. Y equals our slope times x plus our y-intercept,
which is the same thing that we got using the point slope. So oftentimes the point slope's easier, but it really just depends. So now let's try examples of parallel and perpendicular lines. We want to determine if the lines are parallel, perpendicular, or neither. A quick way of doing that is to put all the lines in slope-intercept form. In other words, solve for the y or the output value. That way we can immediately look at the coefficient of the x, which is your slope, and compare. First example here, I'm going to subtract 3x from both sides. So we get 6y equals a -3x plus 21. I'm going to divide everybody by 6. And I get y equals a -1/2 x plus, and it really doesn't matter what your y-intercept is unless they happen to be the exact same b for both lines. So that reduces to what, 7/2? So our first slope here is a -1/2. So let's take a look at our next equation, the 2x minus y equals 7. If we subtract 2x from both sides, we get a -2x plus 7. We're going to divide both sides by the coefficient of that y, which is a -1, and we get y equals 2x minus 7. So the slope of this guy is a +2. Well, we could write that 2 as a fraction, 2/1. Notice both of these are opposites. One's positive, one's negative, and they're reciprocals. That means they are perpendicular. Let's do the same thing for the 2 lines here in B. We're going to subtract 2x from both sides because we want to get this y by itself. So we'll get 5y equals a -2x plus 9. Divide everybody by 5. We get a -2/5 x plus 9/5. So the slope here is a -2/5. On the second equation, again, we're going to subtract 5x from both sides. So we get 2y equals a -5x plus 3. Divide everybody by 2. We get a -5/2 x plus 3/2. So this slope is a -5/2. Well, these guys are not opposites, okay? Opposites, nope. They're reciprocals, right? But they have to be both. So this guy is neither perpendicular, because it doesn't have both, and it's not parallel because they're not identical. They're not exactly the same. See, they've already put it in mx plus b format for both of these. They just put it in function notation. So the slope for this first guy is 3, and the slope of this second guy is 3. Since they are the same, then we know that these 2 lines are parallel. Now in example 3, we're wanting to write the linear equation that passes through the point -2, 5 and is perpendicular to the line y equals 3/8 x plus 1. This information is only to give us the slope.
Because notice they only gave us 1 point.
In order to find the slope, we need to have 2 points, or they need to give us some other information, like it's parallel or perpendicular to another line. So if our line is perpendicular to this line, whose slope is 3/8,
then that means our slope is going to be a negative
8/3, because it has to be the opposite sign and reciprocal.
So again, we can use the point slope equation. We can plug in our XY value that was given, the -2, 5. So we would get y minus 5 equals our slope of a negative 8/3 times x minus a -2. Remember, minus a negative is plus a positive. So we get y minus 5 equals, let's distribute, and we get a negative 8/3 x minus 16/3. Remember that 2 is like a 2/1. And then we have to add 5 to both sides. And we would get y equals negative 8/3 x. And it would be helpful to rewrite that 5 so we can add these two together. So in order to combine those two, we're going to have a negative 16/3 plus, I'm going to change that 5 to 15/3. Negative 16/3 plus 15/3 gives us a negative 1/3. So that is our B.
Now we talked about slope being the rate of change when we're dealing with lines. And that is true. If it is a line as the graph or the equation that we're working with, it is a rate of change. But a lot of our functions are not lines. So we use that linear equation for that slope equation to find an average rate. So some formulas and notations for slope.
We knew the m, the y2 minus y1 over x2 minus x1. You might also see delta y over delta x. Delta just means change. So change in y over change in x. And it could be an average rate of change.
So you might see some different notations for slope or average rate of change. So if we're focusing on finding the average rate of change of this graph that is not linear, but a parabola. Well, as you look at this graph, if I pick different points, the rate of change between those points, in other words, the slope between those 2 points could change. It could be positive if I pick 2 points on the left. It could be 0, or it could be negative. So that's why we're using the word average for any graph or function that's not linear. So we can find the average rate of change between these 2 points by finding the slope of the line that goes through those 2 points. This is called a secant line. If anybody has taken trig, don't get it confused with a secant function. This is referring to something else, okay? So a secant line just goes straight through those 2 points. So let's find the average rate of change, which would be the slope between these 2 points. So we can do -4 minus 2, those are the y values, 2 minus the -1. So we get a -6 on top. Remember, minus a negative is plus a positive, 3 on the bottom. And we get an average rate of change of -2 for just those 2 points. Example 5 is an example of linear modeling. The desired heart rate for cardiac health during exercise is a linear function. So it's nice that they told us that it's linear, of a person's age with the desired rate of a 50-year-old person equaling to 136 beats per minute, and with the desired rate increasing by 8 beats per minute for each decrease of 10 years of age. Okay, wow, that's a lot of information, right? So they're wanting us to write an equation of the function where t is representing age and h is representing the desired heart rate. Now notice they did say that the heart rate is a function of the age. So the heart rate is a function of the age. Now, you may be struggling a little bit because you have an increase of 8 for a decrease of 10 years in age and a desired rate of a 50-year-old person. So you might read this and you say, okay, I know if we start at 50, like that is our baseline, 50-year-old person, our heart rate should be 136 beats per minute. So that means if T is the age since 50, or the number of years after 50, so that's going to be our y-intercept, in other words. Our beats per minute, we know, is going to be 136 beats. That's our fixed, 136 beats per minute. But that heartbeat is increasing by 8 beats per minute, but a decrease of 10 years in age. So in other words, that slope, that change, the heartbeat's going up, but the age is going down. So that gives us a slope of 4, -5. So we have a -4/5 heartbeats for every year of age that you increase. Now, a lot of people may be struggling because of two things. Beats per minute, that sounds like a slope, right? Beats per minute, that's what we were talking about. That's how we can tell it's a slope. But we have two pieces of information here, age and the heartbeat. That's our output, beats per minute. So we want to know, how is that heartbeat changing based on a person's age? So it's beats per minute per year of age. So here's something else that you can do in an example like this. Remember, to find your slope, you need 2 points. So if you're not sure about that 8 and -10, then let's go to our points. We have age and we have heartbeat. We know a 50-year-old should have 136 beats per minute. What else did they tell us? They said that the desired rate increases by 8. So if we increased that heart rate by 8, that would give us 144 heartbeats. But for a decrease of 10 years in age, so instead of a 50-year-old, a 40-year-old should have a heartbeat of 144. So now we've got 2 points. To find our slope, we can do the 144 beats per minute minus 136 over the age of 40 minus 50. So that gives us +8 over a -10, which is a -4/5 slope. Another key is to not use 50 as our age, but use 50 kind of as our starting point. So our time t would be the age since 50, kind of like t would be the number of years since 2010 or something like that. So to check it out and to make sure that this function, works, again, we found our slope of a -4/5. Let's try h of, let's say, what did we come up with over here? Age of 40. So if it's the age since 50, we could plug in a -10. So that would represent the age of 40, 10 years below 50. So we get 136 minus 4/5 times a -10. That gives us 136 plus 40 over 5. So we get 136 plus 8, which is in fact 144 beats per minute. So then it says, what does this function give as the desired heart rate for a 75-year-old person? Now, just to clarify, this is our equation, but you do need to have this. You do need to say that, you're not plugging in someone's age, we're actually putting in t as the age since 50. So to answer B, we're going to use that equation, but what does our t need to be? If t is our age since 50,
then 75 would be 15 years. No, 25 years. 25 years since 50. So we're going to find H of 25. So 136 beats per minute minus 4/5 times 25. 5 goes into 25 5 times. So we get 136 minus 20, which is 116 beats per minute. So a 75-year-old should have a heartbeat of 116 beats per minute during exercise. Pardon my handwriting, guys. Squeezing that in there. All right, I hope that helps, and I will talk to you guys soon. If you have any questions, contact me or your teacher. Get some help. That's what we're here for. Bye.